Hello, welcome to another video. In this video I'll be proving circle theorems. These are the 8 standard circle theorems that you see in GCSEs, so you need to understand what the theorems are and how to prove them. Okay, so the first one is angle at the center. So this theorem says the angle at the center is twice the angle at the circumference. Now when they say angle at the center, they are talking about this angle here, and the angle at the circumference is this one over here. So this angle is twice this angle up here. Okay, so let's talk about how you can go ahead and prove this. And one way to help you to remember kind of how to prove a lot of these theorems is you need to generally add something in. So for this one, we're going to add in another radius. Okay, so this is from the center of the circle to the angle at the circumference. And so what this does is creates two isosceles triangles because these are all radii of this circle. So these sides are all equal, therefore the base angles of each triangle are equal. So I'm going to go ahead and label this angle here, and these two here. So I'm going to call this one A, this one B, this one C, and this one D. And another way of doing this is you can label the points, so you could call this A, B, and C. It's really up to you. I just prefer to label the angles like that, but that's not really that important. It's more important that you understand the theorem and the proof itself. So the first thing we want to do here is to say that, well, if we call this angle C, this angle over here would also be C. I'm not going to label it, but we just know it would be C. So we can say the angle C, well, two lots of C would be 180 take A because of the angles in a triangle add up to 180. So we can say C is equal to 180 take A and then divide by 2. So it's half of those base angles of that isosceles triangle. Same for D. We can say that D is going to equal 180 take B divided by 2. Then to get an expression for this whole angle at the circumference, we can say C plus D equals 180 take A over 2 plus 180 take B over 2. Okay, then if we want to simplify this, we could just add the numerators because the denominators are the same. So we'll get 180 plus 180 is 360, and negative A plus negative B would just be negative A take B, and that is all over 2. So we have an expression now for C plus D, that is that angle at the circumference, this one up here. And now let's think of an expression for this angle at the center. Well, angles around a point add up to 360. So I'm going to label this angle E and say that E equals 360 take A take B. Right, so 360 take this angle and subtract this angle as well, and we'd be left with the angle E. So now we can see, well, this angle at the circumference is 360 take A take B divided by 2. The angle at the center is just 360 take A take B. So therefore this angle is half of this angle at the center, or we could say E equals 2 lots of C plus D. And so that's the proof of the angle at the center being twice the angle at the circumference. And the next theorem, this theorem is called angles subtended by the same arc. So this theorem says angles in the same segment are equal, or you can also say that angles subtended by the same arc are equal. They're two names for the same thing. Personally, I prefer angles subtended by the same arc. It just makes a little bit more sense to me. Because subtended means if you look at this arc here, this one going around like this, ending at these 2 points, these lines here would be subtended by that arc, meaning these lines leave and join up to the ends of that arc. So if you have an angle subtended by that arc and another angle subtended by the same arc, they're going to be equal. So that's always helped me to remember that theorem better than this title here. But anyways, let's go ahead and prove this now. So if we draw the center of this circle, now I don't know exactly where the center is, but let's just assume it's about here. And then let's draw in this angle at the center. So going to the points where these angles join to the circumference. Well, if we called this some angle, let's say that's 2 theta, then we know this angle at the circumference must be half of that angle. So this would be theta up here. And this angle here is also related to this angle at the center because they're joining the circumference at the same place. So this angle over here would also be theta. So based on this angle at the center theorem, we can say those two angles subtended by the same arc must be equal. So let's just go and summarize that as clearly as we can. So let's say as angles at the circumference are half the angle at the center, all angles at the circumference subtended by the same arc are equal. So that's all you really need for the proof of this theorem. It's mostly based on the angle at the center theorem. So if you're ever asked to prove this, you're going to have to either reference this theorem or prove this theorem. All right, that was the first two theorems. Next one is angle in a semicircle. Now, some people consider this the same as angle at the center, right? Because if we look at this triangle here, well, firstly, the theorem says that the angle in a semicircle is 90 degrees. So if you have a diameter, whatever angle you draw from the ends of that diameter, if it touches the circumference, it will be 90 degrees. So the angle in a semicircle is 90 degrees. And as I was saying, some people consider this the same as the first theorem, angle at the center, because if you look at the diameter, so typically you would have like a shape like this, right? You get some angle at the center. And even if you have a diameter, so the line is straight, there's still technically an angle at the center, right? It's 180 degrees at the center. And therefore, the angle at the circumference is half of that, it will be 90. So some people think that this should generally just be considered the same as angle at the center, and that's kind of one way to prove it. But you can prove this another way as well, but it's really essentially a proof of this first one here. It follows along the same lines. So let's go through it again anyways. So we can draw another radius from the center to the angle at the circumference, and these will all be the same length. And then let's go ahead and label some angles again. Let's call this one A, this one B, this one C, and this one D. Again, we can say that C equals 180, take A divided by 2. And same for D equals 180, take B divided by 2. Then we can say that angle at the circumference will be C plus D equals 180 plus 180 is 360. Take A, take B divided by 2. And because we know this line is the diameter, we know A plus B must equal 180. So A plus B equals 180 degrees. So if we look at this expression here, another way of writing this is 360 subtract A plus B. So if you factorize a -1 out of both those terms, so if I plug this in to this expression, A plus B is 190, plug that in there, C plus D becomes 360 take 180 divided by 2. 360 take 180 is 180 divided by 2 is 90 degrees. That's another way of proving that theorem, along with the fact that it's essentially angle at the center. Okay, next one, angles in a cyclic quadrilateral. This theorem says opposite angles in a cyclic quadrilateral add up to 180 degrees. And a cyclic quadrilateral is a quadrilateral that has all of its corners or vertices on the circumference of the circle. Okay, so how do we go about proving this? Let's draw in the center of the circle, and then let's draw 2 radii to opposite corners of that quadrilateral. So we kind of split this up into 2 separate quadrilaterals. Let's label some angles. Let's call this one A, this one B, this one C, and this one D. The first thing we can state is angles around a point add up to 360, so A plus B equals 360. And then if we divided all of that by 2, we could say half A plus half B equals 180. Now looking at D here, in relation to A, it is the angle at the circumference. If this was the angle at the center, this is the angle at the circumference, and therefore we know that D is half of A. So we can say that D equals half A. And also C is related to B here. Even though it's a reflex angle, this still works. So we can still say C is half B. So C equals half B. Therefore, these two angles here added together, C plus D, equals half A plus half B, which we've already said is 180 degrees. So that's going to be 180 degrees. So there we've proved that the opposite angles in a cyclic quadrilateral add up to 180 degrees. Okay, next one is perpendicular bisector. This theorem says the perpendicular from the center to a chord bisects the chord. This can also be sometimes stated in reverse. It sometimes might be said something like the radius that bisects the chord is perpendicular to the chord. So you can kind of reverse it like that. But we want to go ahead and prove that if this is perpendicular to this chord, it also bisects the chord. So firstly, let's draw in some radii to the ends of that chord. And we know they're the same length. This time I'm going to label some points. So call this one O, this one A, and this one B, and this one M. So let's look at these two triangles here. Well, we know that the radii are equal. So we know one side of those triangles are the same. We also know that the angle is a 90-degree angle. So that's what's given in the theorem. What we're trying to prove actually is that this chord is bisected. So I shouldn't have drawn these in here. Sorry if that's confusing, but we're trying to prove it bisects the chord. So we've got the radii or the hypotenuse of this triangle the same length. We have a 90-degree angle the same, and we have a shared line here, right? This is the same for both triangles. So we can say if you have a right angle triangle and you have two sides the same, then you have enough information to say that those triangles are congruent. That is a rule for congruence. So we can say these two triangles, triangle AOM and triangle BOM, are congruent. And this is stated as the leg hypotenuse rule for congruence. Okay, so then therefore all sides are equal. Therefore AM equals MB. So this length here equals this length over here. Therefore OM bisects the chord. That proof can also be reversed. So it depends what they give you. If they tell you this line is perpendicular to the chord, you know it bisects the chord. If they tell you this line bisects the chord, then you know it's also perpendicular. So those two things kind of go hand in hand. All right, I hope that makes sense and I haven't just confused you there. But anyways, let's move on to the radius to a tangent. This theorem says the angle between a tangent and a radius is 90 degrees. All right, this is probably one of the more difficult theorems to prove, just because it's a proof by contradiction. So it's a little bit different to the other ones. So this proof starts off by drawing a line from the center to any point, any other point on that tangent. Okay, so what you want to do is to create some angle here with the tangent line. And this is going to intersect the circle at some point. So let's go ahead and label these points O, the end of this line A, B, where the radius intersects with the tangent, and E, where it intersects the circle, C, where the other line intersects the tangent, and D, the other end of the line. So as I said, this is going to be proof by contradiction. So the main point is going to be if the angle ABO, this one in here, is not 90 degrees, some other angle must make a 90-degree angle with the tangent, because you can always make a 90-degree angle between a point and a line. So between the center and this tangent, there must be some point at which they meet at 90 degrees. So if it's not this one, there must be another point. So that's what we'll start off with by stating. So if angle ABO does not equal 90 degrees, some other angle must make 90 degrees. So then we let angle ACO equal 90. So this one up here. And when we're looking at a right angle triangle, the side opposite must be the longest side. So if you take any right angle triangle, the side opposite the 90-degree angle is the hypotenuse, is the longest side of that right angle triangle. So if we looked at this angle here, ACO, the side opposite that is OB. Right, we've formed a triangle. There's one side CB, one side OB, and one side OC. So we've just let this angle equal 90, therefore OB must be longer than OC. But we know that OB is the radius. Right, we've said that OB is the radius, AD is the tangent, OE is also the radius, therefore EC must be some negative length. Well, that's impossible. So we've hit a contradiction, therefore the angle ABO must be 90 degrees. Okay, so let's go ahead and summarize that. So the side opposite is the longest side, therefore OB is greater than OC. This is clearly a contradiction, therefore no other line can make 90 degrees with AD. Remember, OC is just a representation of any other line we can make from the center to AD, the tangent. Therefore, the angle ABO must equal 90 degrees. Okay, so that was proving the radius to a tangent theorem. Next one is tangents from a point. This theorem says tangents from a point outside a circle are equal in length. Okay, so remember, tangents are lines that touch the circle at a single point. So if they meet outside the circle, the lengths from that point to where they touch the circle will be equal in length. We can prove this by drawing a center and two radii to where the tangents touch the circle. And we've just proved these must meet at 90 degrees. So we can draw our 90 degrees in there, and then we want to draw a line from the point outside the circle to the center. So these are radii. And again, these lines shouldn't be here because I'm trying to prove that they're actually equal. So sorry again if that's confusing. These are both radii, so they're equal in length. We have a right angle triangle, and this line here from the point outside the circle to the center is shared between these two triangles. So these two triangles therefore must be congruent because we have a leg and a hypotenuse equal. Okay, so we can say if we label these points A, B, O, and C, we could say triangles ABO and ACO must be congruent, leg, hypotenuse. Therefore, the other lengths of that triangle must be equal. So therefore, AC equals AB. Okay, so that's tangents from a point. And the last one I'm going to prove is the alternate segment theorem. And this theorem says the angle between a triangle and a tangent through one of the vertices of the triangle is equal to the angle in the alternate segment. So it's kind of difficult to state this in any clear way, but what this actually means is this angle here between the one side of the triangle and the tangent is equal to the angle kind of opposite to it in the triangle. And this will be stated as in the alternate segment. So what I want to prove is that these two angles actually are equal. So one way to prove this is to draw a center and then a diameter through the center, joining the tangent where the tangent touches the triangle, and then join the end of this diameter to the other corner of the triangle. Okay, so then let's label some points. Let's say A, B, C, D, E, F, and let's call D, B, C, let's label that A, and we know this is a 90-degree angle because of the radius tangent theorem. Firstly, let's state some of those things. So let's say that angle CBE equals 90 degrees. We would say radius tangent. Then if you look at the angle BDE, that's the angle in a semicircle. This must be 90 degrees as well. So angle BDE equals 90 degrees. This is angle in a semicircle. Then let's look at this angle in here. So angle EBD, this one in here, angle EBD must equal 90 degrees take A, right? I've labeled that one A. So this little angle in here is 90 degrees take A. Then we want to look at angle BED. BED, this one up here, Well, if this is 90 degrees, this is 90 degrees, take A, we can figure out what BED will be. So angle BED would be 180, the angle's in a triangle, subtract 90, one of the other angles, subtract the other angle here, which we've just said equals 90, take A. So subtract 90, take A. If you work this out, we've got 180, take 90, and subtract negative A would become a positive A. So all we're left with there is a positive A. So BED equals A as well. And if you look at these two angles, BFD and BED, they are angles subtended by the same arc, right? They're leaving from the same points on the circle. So these two angles must also be equal. So we can say angle BFD equals angle BED. And these are angles subtended by the same arc. Okay, so we can also say this is A. Therefore, angle BFD equals DBC, which was what we were trying to prove. Okay, so let's just finish this off. Therefore, angle BFD equals angle CBD, this one in here, the one we called A, equals A. All right, so that was proving the alternate segment theorem, and that was the final theorem that I'm going to prove. So a couple questions you might have: are these the only circle theorems you're going to need to know for GCSEs? Yes, they are. So if you want to make sure of this yourself, you can look at the Edexcel specification or whichever exam board specification your school is using. So this is the Pearson Edexcel specification, and I believe it's on page 17. Okay, here it is, and it says apply and prove standard circle theorems concerning angles, radii, tangents, and chords, and use them to prove related results. Now you might say that's not very specific, given this is a specification. Literally the job of this document is to be specific. Luckily there are other resources we can look at, such as textbooks. This is an official 9-to-1 textbook by Edexcel, and other things such as past papers and the experience of teachers to tell us that these are the 8 theorems that will be covered in GCSEs. While I don't like the fact that the specification is so vague, because it does leave it open to include other more obscure circle theorems, such as the intersecting chord theorem or equal chords theorem, which technically they could include based on this definition, but then nobody would know how to prove them, so I just don't think that's going to happen. So generally we do know that these are the 8 theorems that you need to know in GCSEs and the 8 proofs. So as long as you're okay with these ones, then that's all that you need to know for circle theorems for GCSE mathematics. Now if you would like this PDF with the proofs on it, I'll attach a blank copy and a copy filled out with the proofs in the description, so you can go ahead and download those for your reference later on. Or maybe you want to create your own document with your own proofs set out the way you would like to do them. And I'd suggest that would be a good idea as well. Okay, so I hope you found that useful. Please leave a like if you did, subscribe if you want to see more content, and I'll see you in the next one. Bye for now.